Hello. In this video you will learn how to derive a formula, which is very important and which is widely used in various circumstances. And this is a formula with a very nice history and a very nice geometrical illustration. Let's start. Derivation of a formula, problem number 1. And here is its formulation. Derive the following formula for the sum of first n positive natural numbers and show a geometrical illustration of this formula. So here you see the sum of first n positive natural numbers, 1 plus 2 and so on plus n. And here is the result which we have to show is true. And what about this part here? Well, I introduced this name for this sum, Sn, because it will be practical for me to have a very brief notation for this sum. You will see pretty soon why. And another interesting thing here is this part. This part shows a symbol sigma, large sigma, which is kind of symbolizing the sum. So this letter sigma tells us that we have to sum some numbers, right? And this here we have introduced some variable which I called k, and this k varies from 1 to n. So this number here shows the least possible value of k, and this number up here shows the largest possible value. And this k must take all the numbers between 1 and n. So first k must be equal to 1, and we sum 1, then plus k equal to 2, and so on, and the last term of this sum is n. So this here is a brief notation for this sum. We sum all the numbers k, starting with k equal to 1, ending with k equal to n, where n is just some number. It can be any natural number greater than 1. It can be 1 also, and then you will just have one term here, right? So now you understand this, and you understand that we will prove this formula here. And this formula was already proven in my earlier free course, Mathematics Proofs by Induction. But back then I told you in this course that in order to prove something by induction, you need to know the result. So in this case, you need to know the sum of the formula for the sum of first n natural positive numbers. And in the method which I will show you now in this video, you don't need to know the result in advance, even if we now happen to know what this sum will be. So this is how it looked in this earlier course. If you want to, if you are interested in proofs by induction, you are welcome to register to this course, and you will see me explaining this proof by induction. Okay, but now let's start proving our formula. So what I did here, I wrote down this sum, 1 plus 2 plus 3, and so on. And here you see I also wrote 3 last terms, n minus 2, n minus 1, n. And this is our Sn. And now I will apply a very neat trick. What I will do is write this sum once again, but this time from the largest to the smallest. So here the terms were ordered in increasing order, and here they are written down in decreasing order, from the largest to the smallest. But it's still the same sum, because, you know, the result of addition does not depend on the order of the terms you add, as long as you add the same terms, of course. So now we have this sum twice, exactly the same sum, but written in two different ways. And you see, what I will do now, I will now add these two expressions sidewise to each other, because you know, if two expressions are equal, in this case this expression is equal to this one, and two other or the same expressions are equal to each other, then if I add the left hand side to the left hand side, then it will be the same as adding the right hand side to the right hand side. So I do this, and at the right hand side I get twice my sum Sn, you see, and here if I add 1 plus n, I will get n plus 1. If I add 2 to n minus 1, I will get n plus 2 minus 1 is also n plus 1. N minus 2 plus 3 is n plus 3 minus 2 is also n plus 1. And you see, and it will be the same situation for each pair of numbers standing above each other. So in this way, I got here at the left-hand side just the terms n plus 1 added to each other. And how many times do I have this term of n plus 1? Well, as many times as I had terms here. Right? And I have here n terms, starting with 1, ending with n, and each natural number is present. So this means that I have here n times n plus 1. And this expression, n times n plus 1, is equal to twice my sum I'm trying to compute. So I can write down that n times n plus 1 is equal to twice my Sn. And now I can divide both sides of this equation by, it is actually an equation for Sn because this is my unknown, right? If I divide both sides by 2, I will get just Sn here, and Sn is equal to n times n plus 1 divided by 2. And Sn, as you remember, was just a notation for this sum. So I have my result. I have now proven that this formula indeed is true. And the nice history connected to this problem. History says that Carl Friedrich Gauss, when he was a small boy, maybe 10 years old, I don't know, he was naughty at school, and his teacher decided to punish him by letting him stay after the lessons at school and compute the sum of all natural numbers between 1 and 100. And the teacher thought, well, this boy will be busy for a while. But no, Carl Friedrich Gauss just invented this nice method. He wrote down the sum of all the, well, he probably wrote it exactly as I did, with some points in between pluses, just to mark it that they are more numbers in between, right, from 1 to 100, and then the same sum in reverse order, and well, he was done maybe in 2 or 3 minutes. A surprise for the teacher. And now I also promised you to show you a geometrical interpretation of this formula. So this is, I chose n equal to 6 because it is big enough to illustrate the principle and small enough to fit in my slide here. So you see, here you will see the geometrical interpretation. And this interpretation will be built based on the concept of area. So what I do, I start by taking a unit square, and unit square means that it's a square with a side length of 1 unit. I don't care about if this unit is 1 meter or something else, it's just a unit. So the area of this square is 1 square unit, right? And this area is here. So the value of this area is 1. Then I put 2 more unit squares, and their area together will be 2 square units. Then 3 squares, 4, 5, and 6. You see? In this way, you see that indeed the area of this object here, I don't want to call it triangle because it's not a triangle. You see, this is not a side. This is just some pattern here. So, but the area of this geometrical object is 21. So if you count all these unit squares, you will count, well, 21 pieces. Well, but how does it relate to this number here, which I was supposed to get, 6 times 7 divided by 2? Well, let's copy this object, let's rotate it, and let's rotate it a little bit more. And now let's shift it towards this original object. So I put it closer, and now I put these two together. And what did I get? I get a rectangle with sides 7 and 6. And the area of this rectangle is obviously 6 times 7, right? One side times the second side. And my original object I started with is exactly 1/2 of this rectangle. So this means that its area is indeed 6 times 7 divided by 2. Okay, so now you have learned a very important formula, which is very easy to derive, and this is a formula which is very practical to know. You will see in next lectures we will use this formula a lot in order to derive new formulas. Thank you for watching. Bye bye.